Hello, hello, hello. I hope everyone's doing well today. So we're going to talk about today is work and energy, how they relate to each other, and how they relate within the bigger context of Physics 1. So if you remember in Physics 1 for kinematics, what we looked at was we just looked solely at the motion of objects. So we would look at a ball that was like being kicked, right? So it had an initial velocity and it would fly through the air, and we'd be able to track this trajectory with time, right? And we'd be able to tell different things about it at different points in time, like the acceleration, velocity, and of course its position, right? That's what we cared about. And in the second part, we kind of walked it back a bit, and we looked at the forces acting on that ball. Okay, so maybe it was just like one force, or maybe there were multiple forces that would contribute to that motion, right? But still, we were really only concerned with the motion of the particle. That's really all we cared about, or the motion of the object in this case. Okay. Um, and so with work and energy, we're still going to do that too, but we're going to do it in a slightly different way using definitions from before. So how we're going to do this is we're going to talk about force again. We're going to talk about force, and we're going to talk about it in a slightly different way. So when we apply a force to something, it matters not only the direction and the amount that we apply, but it matters through the duration of the motion. So if we're moving this box here to the right and it's moving, do we push it once or do we continuously push it? And that is basically a new term. So do we push it through its displacement? So through here, we'll just call this displacement. If you remember, displacement is the net change in position, right? You go from x, you go from the final position to the initial position, so we just call that delta x, right? So you go from final minus initial, where this is final position, this was the initial position. And so we call this a new term, okay? We actually call this the work, okay? And what work is work is the equation ends up being this. So work is the force, and it's the dot product into the displacement, okay? And I'll talk about what that is. So this actually isn't multiplication, this is a dot, okay? And if you remember, at the very beginning of the course when I was talking about vectors and different things you could do with them, I mentioned you could quote unquote multiply them. This is one form of that, but it's not quite multiplication. In fact, multiplication is the really wrong term for it, but I'll talk about what it is. So essentially a dot product is a measure of how similar two vectors are, okay? And in this case, the two vectors we're concerned about, whoops, forgot to put a displacement as a vector, because displacement is a vector, right? It's going to the right, that's the displacement. It's a measure of how similar two vectors are. In this case, we're concerned with how similar force and the displacement change is to each other. So what I mean by that is, let's say we're pushing this box, and this box is going like crazy or something, right? And through that displacement, so we'll just call this displacement, okay, so this is the displacement. The force, maybe the force is this way. How similar is this vector to these various, here, let me do this. How similar is this force vector to the different displacement vectors over time? Okay. And that's what work tells us. So it's not just that you applied the force. Work is how you apply the force. apply the force relative to the displacement. Okay. So that's what a dot product physically means, but how do you do it mathematically? So what we can actually do is a little trick here. If we want to know how similar two vectors are, right? What we can do is instead of a dot product, okay, this can actually simplify to just the magnitude of the force times the magnitude of the displacement, so the amounts, right, times cosine of theta. And you must be wondering, why cosine of theta? Well, if force and displacement are in the same direction, and the angle between them is 0, so theta equals 0 in this case, then cosine of theta, or cosine of 0, equals 1. And so we get the maximum amount of work for that, right? Because then it would be work equals force times cosine of 0 degrees, which is just Fx. Whereas if they are 90 degrees apart, so maybe the force is this way, but your object is moving in the other direction, then it would be cosine of 90 degrees. So then it would be 90 degrees in between them. And cosine of 90 is actually 0. So the work done, there wouldn't be any work done. And so when you're calculating work, all you are really doing is you're just putting Fx and then cosine of the angle between force and displacement. Okay. So what does this actually tell us? Okay. What does this actually tell us about pretty much anything? Well, first let me just, so we've defined it. We've said work is how similar two vectors are. In this case, the two vectors are force and the displacement of the object. Okay? But there's a couple other things about work. Number one, it's a scalar, which means it's not a vector. So when you dot product two forces like this, notice none of these guys are because you're just doing it in terms of magnitude now. This guy is just a number. Okay, so you're just going to get a number for it. You're not going to get anything else. Okay, so it doesn't have direction. It's just a magnitude, no direction. Okay, it has units of a Newton meter, and that's because force, it gives you units of newtons. Meter gives you units of displacement, right? Or displacement has units of meters and force has units of newtons. It can also be positive, just like numbers, and negative. Or even 0, just like a number. And we saw the case where it's 0. The case of a negative work would be maybe you're discussing the work of friction. So the object is being pushed in this direction, but friction is acting in this way. So the object is moving to the right. This guy is moving, or the friction's acting to the left. So your displacement's to the right. And so when you do this, it would be cosine of 180 degrees. And this guy is -1. So this can give you a negative work. Okay. So what is work then? like I've told you that it's just the dot product or how similar two vectors are, but what is it really? So well, to answer that, I think the better way to do it, um, whoops. I think the better way to do it is to derive some terms. So let's do a couple derivations, and this will, maybe show you what work actually is. Okay. So let's start by taking the net work on something. So if you remember what net is, this is the sum of all work, right? So whenever you're taking the net of anything, it's the sum of all of it. And so if we're doing that, what we're going to do is we're actually going to replace it with the net force. So maybe there's tons of forces acting on an object. Maybe we've got, something like this. We've just got multiple forces acting. We want the net of them, right? So do you remember summing the forces, right, in the x and y direction? That would be what F net is. And then the displacement, x, let's just say it ends up moving in the x direction. Okay, so we'll just throw in the displacement x. Although I will say this can be, right now we're looking at this one-dimensionally, but you could do x and y, and how you do x and y is you just call it like an r vector, which is like the sum of the x and y motion, right? And then we have our cosine theta in the middle, or in the middle at the end. So if you also, so what we have here is just this equation, W net equals F net x cosine theta. But if you remember, this F net is equal to something else, what we spent our entire last unit doing. This is Newton's second law. So we can plug in the mass times acceleration of an object there. And so we can get and if we truly want the, I hate to make a joke, max here, right? We can just say that the angle between the net force and the displacement is 0, so we can just call this cosine 0 degrees, so we can just call it 1. So we can say the work net equals max. Okay, that will help us just simplify it. So now we can see that work, we still don't know what it is, but we know that it can be equal to the mass times acceleration of an object, the net work on something. Could be the mass times acceleration of the object times whatever it's doing with its displacement. So we're starting to get somewhere. So mass we can't really do too much with. Displacement we can't do too much with. But let's look at A right here. Or actually, let's look at the combination of AX. If we look back to kinematics, so we look back. There's an equation out there that actually has AX in it. It was this one, right? Specifically, right there. So let's go ahead and just subtract this guy over. Doing that wrong. Wait, I said I was going to subtract it. I'm stupid. There you go. And then we're just going to divide by 2. So 1/2 v final squared minus v initial squared equals AX. And so now what we can do is we can plug that in right there. So we can say work net equals max. And what we can do is sub in right there. So we get the net work on something equals 1/2 m. Here, let's just do it like this. M v final squared minus 1/2 m v initial squared. So now we have work net in terms of the mass and the velocity. Okay. But that's still what this basically tells us is notice this is a difference between the two. So the net work, you still don't know exactly what it is, but the net work on an object increases its velocity. That's what the math tells us, right? But if you think about it, this is pretty obvious, right? So if you're pushing something, right, you're applying a force over a distance, which is applying work to something, you increase that object's velocity, and so it moves, right? So that's interesting, but, right, so you push something, it increases and moves, right? That's pretty obvious. You push something and it moves. So let's keep going. Let's keep going and do more with work. Okay. So let's try, so we did the net force last time. Let's try specific forces. So in this case, let's try gravity first. So if you remember, the force of gravity equals mass times gravity, okay? And so what we're going to do then is we're going to just plug this into the work equation. So plug work equals Fx cosine theta, right? And let's say if we're plugging in gravity, so let's say what we're doing is so the situation is we are lifting up an object. And if you look at the free body diagram of that, oops, right, so I don't know if I can draw a hand, but let's just say you're lifting something up. So you're pushing on it, right? So you've got Fn pushing up and you've got gravity pushing down. I mean, it's not accelerating, you're just moving at a constant rate. And so in this case, Fg equals Fn equals mg, right? If you're moving at a constant rate, they're perfectly balanced, they're perfectly in equilibrium. So if we make this equation then, and you're lifting it, right, and it's moving in this direction, this would mean that the work equation would look like mg for the force, right, as we saw right here. The displacement, let's just call the displacement y, just because we're moving in the y direction now. We don't have to, but y final, y initial, right? We'll just call this y. And then the angle between them, because it's in the same direction, it would be cosine of 0 degrees. So the work of gravity in this case, or the normal force, would be just mgy. Okay. And so one thing I want you to notice, and we could just, if we substitute in what y was, right, it was the final position minus the initial. So one thing I want you to notice about work of gravity specifically, if you're looking at this, it doesn't depend on your path. So the amount of work that you do only depends, mathematically, depends on the final point and the initial point. It doesn't depend on the path taken, right? Mathematically, there's only the y final and y initial in this equation. There's nothing else. So work can only depend on the final position in some instances. So this doesn't work like this in all of them, but it will work like this in this one. Okay. So, i.e., what this also means doesn't So mathematically what that means is, I can lift my cup up and I can lift it straight up, or I can take a crazy path, and I will have done the same amount of work on that cup to move it from here to here. Okay? So forces with this property, oops, are known as conservative forces. Forces that do not have this property are known as non-conservative. Okay. So you must be wondering, what are the non-conservative forces? Well, gravity is a conservative force. And basically how you can tell if something will be conservative or not is whether or not the force constantly points in one direction. So gravity, for us, always points down. It doesn't matter how I'm moving it, it's still going to point down in every direction. But something like friction, for example, wouldn't do that. So if you're moving, so this is an overhead view of you pushing a box on the ground. If you're moving this way, right, friction starts to oppose your motion. So friction points opposite of your motion. So if you're changing your path, friction starts changing the direction. And so friction actually doesn't have this property. Friction does depend on the path taken, right? The amount of work that you put into an object to move it on the floor is dependent on the path, okay? So the known conservative forces are, for us, gravity. The spring force, actually. We'll do a little bit with the spring force. And then the non-conservative would be friction. Okay. If you want, so let's talk about the spring force real quick. So with gravity, when we were doing forces, we used gravity a lot. Like gravity was in pretty much every single problem. And I said it was possible we'd do something with the spring force, but because of time, we never did. But the spring force works the same way you can if you want to derive this. Works the same way as everything else, where you just plug in. And you could do this with virtually any force. You basically just plug in what the force equation is into the work equation. So you plug into work. And what you end up getting is, well, real quick, the spring force is actually equal to negative kx, the force itself. And you must be wondering, why is it negative? It's because when you pull a spring, it retracts, right? So this is a restoring force, is what this is known as. The negative sign, because it restores to its original function. The k is just a spring constant. And what the spring constant is responsible for is just the stiffness of the spring. Okay. So if something's stiffer, it'll have a higher constant. But anyway, so you plug this in to that equation, and what you end up getting is the work for the spring, okay, is just negative, so F spring, right, I haven't plugged it in yet, times X, cosine theta. And the spring force will be in the same direction, so this again will go away. So work spring equals minus kx times x. And so the issue is that the spring force isn't constant. And so what we have to do here is for a force that's not constant, so what happens, and you probably have noticed this, when you're pushing a spring, compressing a spring, especially a really tough spring, it gets harder and harder to compress it the more you do, right? Or pull it apart. It changes as you're compressing it and releasing it. And so how we handle that is we actually divide this guy by 2, so we average it. Because it's not a constant force. And so we plug this in, and what we end up getting is minus 1/2 kx squared. Okay, that's the work done by the spring. And if we want the work done, so the work done by the spring, okay, if we want the work done against the spring, and I'll talk a bit about this when we do example on how you do against it and with it. We kind of did it a little bit with gravity. I was talking about the normal force. But when you see example problems, you'll see how that works. But the work done against the spring would just be you get rid of the negative sign because it's going to be going with the object instead of against it. So the spring force is the opposite the motion, and this one's not. Okay, so now we've got that equation. So we've got 3 equations. So 3 equations that we did so far. We've got work net, right? The net work was 1/2 k. M v final squared minus 1/2 m v initial squared. We had work against gravity, which is also the same thing as the normal force, the work done by the normal force, which was equal to the work of gravity. Mgy final minus mgy initial. And we had the work against spring, which was 1/2 k, and then x final minus x initial. Okay? This should have been delta. Sorry. Okay, so we had 3 equations, and we want to know what is the point. So what did this, whoops. So it showed us several things. It showed us a couple things. So it showed us, one, if you put work into an object, you can change that object's velocity. But it also showed us with other cases, other specific forces, that if you put work into an object, you can change that object's position. Okay? In the case of the spring, you know, you can compress it, right? The position is changing of the spring. Or if you're lifting something up against gravity, it can change its position too. So, number 1, work can change an object's velocity. 2, in specific forces, read conservative, so conservative forces Work can change an object's position irrespective of so it won't depend on the path taken for these guys. Okay. So what does this actually represent then? So what we call the right-hand side is energy. So the right So the right-hand side in all these equations is a form of energy, okay? As, you know, the title of the lecture stands, it's work and energy, right? We've been talking about work this whole time, but we need to talk about how work relates to energy. So in that first equation, work net equals the change in 1/2 mv squared, right? This is known as the kinetic energy of an object. Okay, this is the energy of motion. So this is the energy of motion. If an object is moving, it has what we've defined as kinetic energy. Okay. The second equation, or the next two, have forms of potential energy. Okay. And so what is potential energy? So we have two forms, right? We have mgy final minus y initial, right? And so this is PE1. I'll just call this gravitational potential. Gravitational. And then we have PE for the spring. And so these are forms of potential energy. And so what potential energies are is potential energy can be converted or stored. Here, let me write stored. So potential energy is a form stored and later converted into other forms of energy. Okay? So it's a form of energy that can be stored and later converted into other forms. Whereas kinetic energy is just the energy of motion. Things that are moving have kinetic energy. Things that have, you know, position relative to the ground or relative to what you define as zero would have gravitational potential energy. And if you're pushing against a spring, you would have spring potential energy. Okay? So every conservative force has a potential energy associated with it. We're really going to only look at two, but there are other forms of energy, especially in like physics 2 or whatever, that do have potential energy. Non-conservative forces like friction do not have potential energy. So non-conservative forces do not have potential energy. Okay. But so we've been talking about this. We started off defining work, right? We said work Work is just the force dotted into the displacement, right? It's the dot product of force and displacement. And then we saw that work can be equal, or work can be used to change an object's velocity and change an object's position irrespective of path. We define those things as kinetic energy and potential energy. But now, what is energy? So we've kind of talked about what work is, but we've defined work in terms of, these terms, right? Velocity and other stuff. So energy, the physics energy term, is defined as the ability, you guys may hate me for this, to do work. So if you have energy, you can do work, which means you can apply a force to an object over a certain distance, right? So because I can give energy to this cup, I can move it up, right? I can give it gravitational potential energy by putting work into it. I can change its velocity because I'm putting work into the object, and that changes that object's kinetic energy or the potential or both. Okay? So that's kind of how this will work. So now what I'm going to do is, now that we've seen work equals energy, right? Different kinds, but work does equal energy. What I'm actually going to do, and I'm going to go ahead and just I guess I'll do a very short derivation of this because we've already done a lot of derivations today. I kind of want to talk about more of this. But if we want to create a new equation for the net work, we know that net work, what we did before, right? Net work equals to the MAX, right? And that's how we ended up getting the kinetic energy. So net work equals the change in kinetic energy. But what we can also do is write net work in terms of another expression, a more generic expression. And to do that, what we can do is say that the net work is equal to the work due to conservative forces acting on an object, but also the non-conservative forces. So if you're pushing an object, right, you're pushing it up against gravity, that would be a conservative force. Or maybe you're pushing against friction, and that would be a non-conservative force. And so all those things are doing work on that object, whether they be positive or negative. And so if you actually go through, and I do this notes, but basically what this ends up being is trying to decide if I want to derive this. What we can do is, for the conservative work, what we can do is we can write conservative work in terms of the potential energies, gravity plus the spring, right? And then for the non-conservative work, this would be work like the work of friction, okay? But we'll just leave that there for now. But we can also add in the change in kinetic energy here. And so what we can actually get, so delta, 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 what we can actually get is an equation known, what it ends up being after you actually do all the math with this. And I just trying to save you some time because the derivation is not super essential. What this ends up giving you is this equation where the initial energy of an object, the initial energy of a system, is equal to the final energy of the system after you subtract away the non-conservative work from the system. So non-conservative work will always subtract away from the system. Sometimes it can add to it. So for example, think friction. So I'm pushing an object, right? That has initial energy. if you're pushing it, right, there's friction, and friction subtracts away from the system, which would be here, and that gives us the final energy total in the system. So what this is known as mechanical energy conservation, okay? Where the initial energy in the system is equal to the final energy in the system if there's no non-conservative work to either add to the system or subtract away from the system. And so what ends up happening then, how this ends up working is that you have an object. So here, let's just say it like this. So how this all works, kind of like a summary, is you put work into an object, okay? So maybe you push the object or whatever. You put work into the object. That object now has energy in the form of kinetic energy and potential energy. And okay, let's just do it like that. So you put work into an object, you push an object. That object now has energy in the form of kinetic energy and potential energy, possibly, doesn't have to, but it has forms of energy. So now that object can now do work on the environment around it, okay? So that object moves, maybe it hits something else, transfers that energy. So as energy is transferred from you to object to environment, no energy is lost, okay? In other words, there's energy conservation. So you push an object, that object now moves, does stuff around it, and then it can do work on other things. That object won't lose energy because it's all accounted for. The energy initial will equal the energy final if there's no non-conservative work. So if non-conservative work, okay? So like friction, air resistance, whatever. And what we're going to do is we're going to do problems with both. So we'll see. We'll put work into an object. That object will now have energy, and then we'll see how that object, its energy can change over time and things like that. And we'll use energy to track the motion of objects. Okay, which is a different way of looking at it, as opposed to forces and kinematics. And I should also mention, now that we're talking about energy, energy, one last thing I forgot to mention, is also a scalar, because work is, which means energy also has, and this is why some people like working with energy more, because you don't have to deal with vectors, which can be annoying for some people. So energy also has units of Newton meter, and we also call these joules. Okay. One last thing I forgot to mention is the relationship. I know I keep forgetting to mention and stuff. This isn't a huge deal, but I want you to know the name of it because it's sort of an important theorem. The relationship between work and energy is known as the work energy theorem. Okay. So that's pretty much it. I'll see you guys in the next one where we'll work some problems and you'll kind of see how this all works. Thanks for watching, and I'll see you in the next one.